Howdy folks. We had a bit of a magical moment in class yesterday where somehow everyone seemed to understand the relationship between covariance and significance of independent coefficients and R-square in regressions and multiple regressions and hierarchical versus forced entry regressions yesterday with a silly sort of example, so I wanted to try and recapture that today in what I hope is going to be a quick video. It's my third time recording this because I tend to blabber a lot, so let's keep it simple. I'll try not to repeat myself a whole lot like I usually do. First, I would like to show you what happens in a correlation versus a regression. We're going to use this data here. It's part of the Jamovi default data library, so you can follow along with me. First, let's run a correlation. A correlation is the simplest type of regression, and we're going to see, does neuroticism overlap or move together or correlate with agreeableness? Those all mean the same thing, and we see that there's a significant correlation here. It's less than p.05, and it's not that strong. A strong correlation would be minus 0.7 or plus 0.7, but it is there. We know it's there. It's probably significant because we have a lot of data in this data set. But it's kind of right on that border of significance. If we run a regression, instead of just having one R and a p-value, we will have R square and a p-value for the coefficient. These are two different types of significances for the same thing that's going on. You notice that the R is the same. This time it's not negative, but the p-value is the same. And this R here is very important in a regression. That indicates the amount of variance that your independent variables altogether explained of your dependent variable. Right now, there's just one independent variable, so our R square isn't too big, and this one independent variable isn't too strong, so that's why it's also not too big. We know it's not too big because the original R wasn't too big. We can check the significance of this R square with the overall model test. The reason we have a p-value for this is because we have, if we run a regression with multiple independent variables, a significance for each independent variable, just like you have in an ANOVA, but also a model significance. How well did every variable explain the dependent variable working together? You'll notice that when we run this regression, at first, agreeableness is significant, and I'm saying that's kind of on the border of significance. And if we add other independent variables to it, agreeableness becomes just not significance. It loses significance there. Why does it lose significance? Why does the R square only increase? And why is our significance still exactly the same if R square got stronger? Shouldn't things be more significant? Was it actually exactly the same? I think it did actually get a little bit more significant. Yeah, it did. So scratch that last part. Let's see how variance in that regression works through an explanation, and then I'll give you the example that really seems to solidify everything. Back to a correlation, the simplest type of regression. When you run a correlation, you are comparing the relationship between your independent variables variance and your dependent variables variance and your independent variables variance. And you can say that the more they overlap, the more significantly they correlate. The way that you identify that R, or really R square, is to compare the covariance, the shared variance of these two, to the overall variance of the dependent variable, or the unaccounted for variance of the dependent variable. The R square is a percentage of accounted for variance. So it's covariance divided by all the variance, or you can also think about it like the relationship between what was accounted for by your independent variables versus what wasn't accounted for in your dependent variable. This gets more complicated when we run a multiple regression which involves two or more independent variables. But it's not that much worse off. Imagine that we add in another independent variable. What does that do to these covariances? Well, we get a series of different covariances. We have just the unique covariance. How much does independent variable 1 overlap with dependent variable that isn't overlapping with your other independent variables? And this unique covariance is now the significance of the coefficient. This shared covariance here is tossed, ignored, when you're checking for the significance of your independent variable coefficients. But all of the accounted for dependent variable variance is included when checking for the R-square or overall model significance. This is why when you add in another variable, variables can lose significance if a lot of their covariance becomes shared covariance and is then ignored. This is also why when you add in a variable, another variable can become significant. In that case, there's less unaccounted for variance thanks to what this guy did, and this guy would not have lost a lot of unique covariance. So adding in a variable that makes a previously non-significant variable more significant happens because there is less unaccounted for variance compared to the unique covariance in that first original variable. So it's possible for variables and coefficients to become more or less significant with each added variable in a regression. However, you are never going to overlap less with your dependent variable when you add in an independent variable. So your R-square is only ever going to stay the same or go up. Yeah, that says what I was just talking about. Here are the formulas that I've verbalized so far. The significance of independent variables or their coefficients is the ratio between unique covariance and unaccounted for variance, whereas the significance of R-square, or just your R-square, is the accounted for dependent variance divided by the total dependent variable variance. Now here's the example that people seem to like. You can imagine that the variance we're working with here is much like asking the question, how much food did people eat at my party? If you ordered 500 pounds of food and people ate, say, 300 pounds of food, then 60% of your food was eaten. In the same way, if the independent variables in your regression account for 60% of your dependent variable variance, you're going to have an R-square of 60%. 60% of my food was eaten. However, if you want to answer the question, who ate the most food, or did any one person eat a significant portion of the food at my party, then what you need to look at is just the food that an individual ate by themselves. We're just going to pretend that any food they shared is not included in this calculation, because that's too complicated. The real reason is because independent variables are supposed to be independent. So any shared food is completely ignored. This is pretty much how your forced entry regression decides significance for your independent variables, decides the R-square. How is this different from a hierarchical regression or a blocked regression where you include one or more variables in a series of steps? That looks What does that say? Shared covariance affects R squared, not independent variables of significance. I already talked about that. So what does the hierarchical or block regression look like? It looks like this. Basically what happens is you have a predilection. You think that for whatever reason, a certain variable deserves to be given a better opportunity to account for the dependent variable than another one. This is kind of like saying, my cousin Tina is huge, and I know that she probably ate more than her fair share of stuff. So any food that she ate and any food that she says she ate, probably we should just say she ate it. In this hierarchical regression, variables entered in an earlier step or in an earlier block are given all of the R square that they could possibly get, and later variables or later blocks are given only as much chance to account for R square as they can without overlapping with the previous blocks. That being said, the significance of each independent variable coefficient is still the same. It's still just based on that unique covariance. Let's go back to Jamovi and let me quickly show you that. Remember, we've got this regression where agreeableness is just barely not significant. We're accounting for R square 25% of neuroticism with these 4 variables. Is there any way that we can check what agreeableness does and give it all the opportunity to be significant? We can do this with a hierarchical regression. We're going to create a new block and let agreeableness be in the regression in the first block or the first step. This is going to give us 2 models. The first model is just agreeableness, like we had before, it's significant. And we have our R square of 0.018, like we had before. But we also have this second model, which includes block 2 and block 1. Now agreeableness, just like in the forced entry regression, is not significant anymore. But what we see is how much did extroversion, openness, and conscientiousness add to the model after agreeableness was given the best shot it could be given. We increased our R square from 0.018 to 0.254. The overall model is more significant, and if we look at the delta R square change in model accounted for variance, our R square increased by 0.236, or 254 minus 018. The improvement in the model, or the improvement in the explained variance of neuroticism, thanks to block 2, extroversion, openness, and conscientiousness, was a significant improvement. Let's do one more thing to finish off. If we put agreeableness in the model after these 3 variables, we can check whether it adds anything significant to the model despite not being a significant variable itself. You'll notice the change in the model, the improvement, is not significant. In fact, it's very similar or the exact same as the coefficient significance, which might not be a surprise. But if you're doing something like this, where you might say, oh, well, openness and agreeableness both suck, but do the weak variables add anything to the model even after accounting for the stronger variables? And together, they do. Not a lot, but they improve their model at least a little bit. So in conclusion, remember, even if what you do isn't over and above better than what is already there, if you try hard and work with other people, you can make a significant improvement in the world. Isn't that grand? Have a great day, y'all, and remember that it doesn't matter how many people or how much food was eaten at your party, as long as you're not left over with a shit ton of food. Take it easy.